Swayam Prabha. Digital India. Educated India.
So, in the last class we were discussing the P control of a second order process. In the last class we were discussing the proportional control of a second order process. We will continue that topic today. So, P control of a second order process and we will consider servo case. Fine. Basically, we want to see the closed loop response of a second order process under P only control. So, what are the different elements of a closed loop process? First element is the process, that is basically the open loop process. The open loop process with second order system has the transfer function Gp, and that is equal to Kp divided by tau square a square plus 2 zeta tau s plus 1. This is the transfer function of a second order process. Second order process. Next element is the controller. Next element is the controller. We are interested to observe the closed loop performance under P only control. Accordingly, the controller equation has the form of Gc equals Kc. Fine. This is the transfer function of P only controller. For simplicity, we will consider Gm and Gf both are equal to unity. The transfer function of the measuring device, that is Gm, and the transfer function of the final control element, that is Gf, are equal to 1. Now, what is the expression, general expression for closed loop transfer function? General expression of closed loop transfer function is represented as y bar equals Gc Gp Gf divided by 1 plus Gc Gp Gf Gm y set point bar plus Gd divided by 1 plus Gc Gp Gf Gm d bar. This is the general form of closed loop transfer function. Fine. Now, considering or substituting all the individual transfer function in this generalized form, we obtain y bar equals Kc Kp divided by tau square a square plus 2 zeta tau s plus 1 whole divided by 1 plus Kc Kp by tau square a square plus 2 zeta tau s plus 1 multiplied by y set point bar, and this is a closed loop transfer function for servo problem. Fine. Substituting all the individual transfer function Gc, Gp, Gf, Gm in the generalized form of this closed loop transfer function, we obtain this form for the servo case. Now, if we simplify it, then we will get Kc Kp divided by tau square a square plus 2 zeta tau s plus 1 plus Kc Kp multiplied by y set point bar. If we divide the numerator and denominator by 1 plus Kc Kp, dividing the numerator and denominator by 1 plus Kc Kp, then we obtain y bar s equals Kp prime divided by tau prime square a square plus 2 zeta prime tau prime s plus 1 multiplied by y set point bar. Dividing numerator and denominator by 1 plus Kc Kp, we obtain this form, where tau prime equals tau divided by root over of 1 plus Kp Kc. Zeta prime equals zeta divided by root over of 1 plus Kp Kc, and the gain Kp prime equals Kp Kc divided by 1 plus Kp Kc. Fine, these are the expressions which have been used in this closed loop form. Now we will conclude. So, due to the inclusion of proportional controller with the second order process, the order does not change, the order remains same. So, we will note down few points. Due to the inclusion of proportional controller, there is no change of order of the overall system. No change of order. Fine, this is the first point. Secondly, if we see the expressions of tau prime, we can say that tau prime less than tau. Fine. Secondly, zeta prime less than zeta. It means overall response under P only control becomes more oscillatory. Overall response under P only control becomes more oscillatory because damping factor is decreased. Fine. As a result, the overall response under P only control becomes more oscillatory. In the last class, we discussed up to this. Fine. So, next we will determine the offset. Next we will determine the offset. Now our closed loop transfer function is y bar equals Kp prime divided by tau prime square a square plus 2 zeta prime tau prime s plus 1 y set point bar. This is the closed loop transfer function which we derived for servo case. Now we will consider a step change in set point with magnitude A. Fine. We wish to determine the offset introducing a step change in set point with magnitude A. So considering this y set point equals A by S, the closed loop transfer function becomes Kp prime divided by tau prime square a square plus 2 zeta prime tau prime s plus 1 multiplied by A by S. Fine. Now according to final value theorem, the ultimate response we determine as limit s tends to 0 s y bar s. Fine. So limit s tends to 0 Kp prime A divided by tau prime square a square plus 2 zeta prime tau prime s plus 1 which is equal to Kp prime A. Fine. The ultimate response for the case of second order system under P only control with the introduction of a step change in set point with magnitude A, we obtain Kp prime A. Then what about offset? We know the offset equals new set point minus ultimate value of the response. So new set point is A, ultimate value is Kp prime A, new set point is A and ultimate value is Kp prime A. So A multiplied by 1 minus Kp prime. Now we will substitute the expression of Kp prime. So A 1 minus Kp prime is Kp Kc divided by 1 plus Kp Kc. What is the expression of Kp prime? Kp prime is Kp Kc divided by 1 plus Kp Kc. So the offset becomes A divided by 1 plus Kp Kc. Fine. This is the offset. Now when the offset becomes 0 or when offset approaches to 0, when Kc tends to infinity. When Kc tends to infinity, the offset approaches 0. Offset approaches 0, but this is not true in practice due to some limitation of Kc value. Fine. Now we will try to produce one plot to observe the dynamic behavior of the closed loop system. We will produce a plot to observe the dynamic behavior of the closed loop process. Now, we obtain the expression of zeta prime as zeta prime equals zeta divided by root over of 1 plus Kp Kc. This expression we obtain. So, with the decrease of Kc, zeta prime increases. Agree? So, with the increase of Kc, zeta prime decreases. So, if we increase the Kc value, the overall response may be more oscillatory. If we increase the Kc value, the overall response becomes oscillatory. So, with the increase of Kc, the overall response becomes more oscillatory. This is one point. Another point is, we know the offset equals A divided by 1 plus Kp Kc. The larger the Kc value, the smaller the offset. From this expression, we can say that the larger the Kc value, the smaller the offset. The larger the Kc value, the smaller the offset. Fine. Now, considering these 2 points, with the increase of Kc, the overall response becomes more oscillatory, and another point is, the larger the Kc, the smaller the offset. We will try to produce the plot, I mean the closed loop response, keeping in mind these 2 points. So, we will produce y versus time, y and y set point we will consider, and here time. Now, we consider a step change in set point with magnitude A. So, this is magnitude A. Initially it was say 0, and we are introducing step change at time equals 0. Now, the closed loop response is like this. For a particular Kc, that is suppose Kc1, this is for another Kc, suppose Kc2. So, here Kc1 is greater than Kc2, fine. So, for the large Kc, that is Kc1, we obtain more oscillatory response, one point, and second point is, for large Kc, the offset is relatively small, and this is for the case of Kc2, offset is large for small Kc, fine. So, the above 2 points are taken into account in the development of this closed loop response, fine. In the next, we will discuss the effect of integral control action. So far, we discussed the effect of proportional action on the overall response of a process. In the next, we will discuss the effect of integral action on the overall response of a process. So, next topic is effect of integral control action. Integral control action, and we will consider servo problem only. Fine, we will consider only the servo problem. The regulatory problem is left for the students. So, we will consider different elements and their expressions first. First element is the process, and to discuss the effect of integral control action, we consider first order process. So, for first order process, the transfer function can be written as Gp equals Kp divided by tau Ps plus 1. This is the transfer function of a first order process. Next element is the controller. Fine, the controller is the integral controller. What is the transfer function of integral controller? The transfer function of integral controller is written as Gc equals Kc divided by tau Is. For PI controller, the transfer function is Kc multiplied by 1 plus 1 divided by tau Is. That means Kc plus Kc divided by tau Is. So, this is the transfer function of P and this is the transfer function of I. Fine. So, if we consider only the integral controller, then the transfer function is Gc equals Kc divided by tau Is. And for simplicity, we will consider the transfer function of measuring device and the transfer function of final control element, both are unity. That means Gm and Gf equal to 1. Now, we will try to develop the closed loop transfer function substituting all these individual transfer functions. In the next, we will develop the closed loop transfer function. The general form is Gc y bar equals Gc Gp Gf divided by 1 plus Gc Gp Gf Gm y set point bar. Now, we will substitute the individual transfer functions in this closed loop transfer function for the case of servo problem. Gc is Kc divided by tau Is, this is Gc. Gp is Kp divided by tau Ps plus 1 and Gp is equal to 1. Then 1 plus Kc divided by tau Is multiplied by Kp divided by tau Ps plus 1 and y set point. Fine. If we simplify this expression, then we obtain y bar s equals 1 divided by tau square a square plus 2 zeta tau s plus 1. Simplifying, we obtain this expression multiplied by y set point bar. First, we substituted all the individual transfer functions in the generalized form of closed loop transfer function. Then after simplification, we obtain this expression, where tau is root over of tau y tau p divided by kp kc, where tau has this expression, I mean tau has this relationship. Similarly, zeta is equal to half root over of tau y divided by tau p kp kc. Fine. So, these are the two expressions which have been considered in the development of closed loop transfer function. You see, from these correlations it is clear that the tau and zeta both depend on the value of kc and tau y. From these two correlations, it is obvious that the tau and zeta both depend on the value of kc and tau y, where kc and tau y are the tuning parameters, controller tuning parameters. In the next we will try to determine, in the next we will determine the offset. In the next we will determine the offset. Now, for determining the offset, we will consider a step change in set point with magnitude a. That means y set point bar is equal to a by s. We are considering a step change with magnitude a. Then the closed loop transfer function becomes 1 divided y bar s equals 1 divided by tau square a square plus 2 zeta tau s plus 1 multiplied by a by s. Then offset is equal to new set point minus ultimate value of the response. We know this correlation, offset equals new set point minus ultimate value of the response. So, new set point is a and ultimate value of the response is how much? A. So, offset becomes 0. Fine. The offset becomes 0. So, we can say that the integral control action can eliminate the offset. It is very obvious from this that the integral control action can eliminate offset. Now, we will note down few important points. Is there any change of order due to the inclusion of integral action? Yes. So, due to the inclusion of integral action, the order changes. The order of the overall system changes. The order of the overall system changes due to the inclusion of integral action. This is the first point. Second point is, we have seen that due to the inclusion of integral action, the offset becomes 0. So, second important point is, the integral action can eliminate the offset. Integral control action eliminates the offset. Third important point is, as I mentioned, zeta depends on the value of Kc and tau y. If we see the expression of zeta, we can say that zeta depends on the value of Kc and tau y. So, closed loop system provides overdamped or underdamped or critically damped response depending on the value of Kc and tau y. Closed loop system provides overdamped or underdamped or critically damped response depending on the value of Kc and tau y. Closed loop system provides overdamped or underdamped or critically damped response depending on the value of Kc and tau y. So, the selection of Kc and tau y is very important. Fourth point is, if we again see the expression of zeta, that is zeta equals half root over of tau y divided by tau p Kp Kc, we can say that with the increase of Kc, zeta decreases. With the increase of Kc, zeta decreases. So, the overdamped response may move to underdamped response due to this. The overdamped response may move to underdamped response with large overshoot and decay ratio. If Kc is sufficiently large, the overdamped response may move to underdamped response with large overshoot and decay ratio. In the same line, we can conclude again that with the decrease of tau y, zeta decreases. You see the expression of zeta, it is clear that with the decrease of tau y, zeta decreases. So, if the tau y is sufficiently small, the overdamped response may move to underdamped response with large overshoot and decay ratio. Fine. Now, we wish to produce plots based on the comments 4 and 5. In the fourth point, we have mentioned that with the increase of Kc, zeta decreases. That means more oscillatory response. So, that we will reflect through this plot, y versus time. A step change is introduced with magnitude A. This is suppose 0 and the step change is introduced at time equals 0. Now, this is the closed loop response for a particular Kc value. Suppose that is Kc1. Another closed loop response we obtain for the value of Kc2. So, which one is greater, Kc1 or Kc2? Kc1, because our fourth point is with the increase of Kc we get more oscillatory response. So, Kc1 is larger than Kc2, that is why we obtain more oscillatory response, but definitely here tau I is kept constant, we only varies the Kc value, we only varied the Kc value. Similarly, we will produce the closed loop response based on 0.5, that is with the decrease of tau I, zeta decreases. That means with the decrease of tau I, the overall response becomes more oscillatory. So, we will try to produce y versus t. Similarly, a step change is introduced in set point with magnitude suppose A at time t equals 0. Now, this is the closed loop response for a particular tau value, suppose that is tau I1. Another response we obtain for tau I2. So, which one is larger? Which one is largest among these two? Tau I2. That means tau I1 is less than tau I2. Fine. With the decrease of tau I, zeta decreases, that means more oscillatory response. So, first one is the closed loop response with the variation of Kc, and second one is the closed loop response with the variation of tau I. So, these 2 points 4 and 5 clearly say that we need to judiciously tune the values of Kc and tau I. We need to judiciously tune the values of Kc and tau I. So, we discussed the effect of proportional action and integral action on the closed loop response. The third action is the derivative action. We will discuss that. I mean, next we will discuss the effect of derivative action on closed loop response. Effect of derivative action, derivative control action. And we will consider the servo problem. in the discussion of derivative action, we will consider the first order process and servo problem. So, in a closed loop block diagram, the important element is process. The transfer function of the process of a first order process can be written as Gp equals Kp divided by tau Ps plus 1. This is the transfer function of a first order process. Next element is the controller. Presently, we are discussing the effect of derivative action. So, the controller is only derivative controller. What is the transfer function of derivative controller? Kc tau ds. This is derivative action. Fine, because the transfer function of PID controller we have written Kc plus Kc divided by tau is plus Kc tau ds. This is the transfer function of proportional action. This is the transfer function of integral action, and this is the transfer function of derivative action. Fine. And for simplicity, we will consider the transfer functions Gf and Gm both are equal to 1. For simplicity, we will consider Gf and Gm both are equal to unity. Now, we will try to develop the closed loop transfer function substituting all these individual expressions. In the next, we will develop the closed loop transfer function, which is expressed in generalized form as y bar equals Gc Gp Gf divided by 1 plus Gc Gp Gf Gm y set point bar. This is the generalized form of closed loop transfer function for servo case. Now, if we substitute the individual transfer functions, then we obtain Gc as Kc tau ds. Fine. Next transfer function is Gp, that means Kp divided by tau Ps plus 1, and Gf is 1, whole divided by 1 plus Kc tau ds multiplied by Kp divided by tau Ps plus 1 multiplied by y set point bar. Now, if this is the closed loop transfer function we obtain substituting all individual transfer functions. Now, if we rearrange further, then we obtain the final form of closed loop transfer function as y bar equals Kp Kc tau ds divided by tau p plus Kp Kc tau d multiplied by s plus 1 y set point bar. This is the final form of closed loop transfer function. Fine. Now, this is the time constant of the closed loop transfer function. So, this time constant we can say, we can call as effective time constant, denoted by tau p prime. So, tau p prime equals tau p plus kp kc tau d. This is called as effective time constant. We can call this time constant as effective time constant. Fine. So, which one is larger, tau p or tau p prime? Tau p prime. Now, we will note down few important points. Due to the inclusion of derivative action, is there any change of order? No. The order of the overall system does not change. We have taken first order process and the overall process is also first order. So, there is no change of order, no change of order of the overall system. Due to the inclusion of derivative action, there is no change of order of the overall system. This is the first point. Second point is regarding the time constant. The time constant tau p prime is greater than tau p, because kp kc is positive and tau d is also positive. Kp kc is positive, multiplication of kp kc, I mean multiplication of kp and kc, that is positive, and tau d is time constant is always positive. So, this is also positive. Therefore, tau p prime is greater than tau p. So, what it indicates? The overall response becomes sluggish, slower. Third point is, as kc increases, then what happens for tau p prime? If kc increases, then tau p prime also increases. With the increase of kc, tau p prime increases. That means the overall response becomes slower due to the increase of kc. Similarly, what happens for tau d? If tau d increases, the effective time constant increases. So, in the derivative action, there are two tuning parameters involved. One is kc, another one is tau d. So, that is why we observe the effects of kc as well as tau d. With the increase of kc, tau p prime increases, and with the increase of tau d, also tau p prime increases. That means the overall response becomes slower due to the increase of kc and tau d. Fifth point is related to the offset. Can you calculate the offset? With introducing a step change in set point with magnitude a. What about offset? Offset is a. So, fifth point is that derivative controller cannot eliminate offset. Derivative controller cannot eliminate offset. These are the 5 important points related to the closed loop response under derivative control action. So, we have discussed about the 3 proportional controllers. One is P only, second one is PI, and third one is PID. Now, we will conclude these 3 control actions one by one. So, first controller is P only controller. What we concluded for P only controller? It speeds up the response. If you see the response of a open loop system and if you see the response of a process, same process under P only controller, we obtain faster response in case of process under P only controller. Fine. If we include a proportional controller with a process, the overall response becomes faster than the open loop response. Therefore, we can conclude that the P only controller speeds up the response. So, it speeds up the response. Secondly, we can say that with the increase of Kc value, the proportional only controller output becomes more sensitive to error. With the increase of Kc value, the P only controller output becomes more sensitive to the actuating error signal. This is the second conclusion on P only controller. Third one is it cannot eliminate offset. It does not eliminate offset. Fine. These are the 3 important points related to P only controller. Next is PI controller. Most important point related to PI controller is that it eliminates the offset. So, it eliminates the offset. So, which part eliminates the offset? Integral part. Integral action eliminates the offset. Second point is the order. For P only controller there is no change of order, but for PI controller the order is increased. So, second point is order increases, and as the order increases the overall response becomes sluggish. The overall response becomes sluggish. Now, how we can improve this situation? Due to the inclusion of integral action with P action, the overall response becomes sluggish. Now, we want to speed up the response. How we can do that? Either by increasing Kc or decreasing tau I, isn't it? We can speed up the response either by increasing Kc or by decreasing tau I. If you see the control equation, PI control equation, it is clear that with the increase of Kc, the overall system response become faster. But if Kc is larger than the certain value, or if tau I is sufficiently small, the process goes unstable. I mean, there may be some instability problem. So, if the Kc value is sufficiently large or tau I is sufficiently small, the instability problem may arise. For the case of PI controller, if Kc is sufficiently large or tau I is sufficiently small, the instability problem may arise. Fine. Next is the PID controller. So, first we can say that it eliminates the offset. PID controller eliminates the offset, and this is definitely the effect of integral action. Fine. Now, for the case of PI controller, we observe that with the increase of Kc value, I mean when Kc is larger than the certain limit or tau I is sufficiently small, there is some instability problem that can be improved by the addition of derivative action. Fine. So, PID controller has better stability criteria. PID controller has better stability criteria, and this is due to the derivative action only. Fine. Third point is, if error is constant, then there is no derivative action because d epsilon dt is there. If error is constant, then there is no derivative action. And last point is, for a noisy response with almost zero error, the derivative term leads to large control action, although that is not required. For a noisy response with almost zero error, the derivative term leads to large control action, although that is not needed. Fine. So, these are the concluding remarks on 3 proportional control actions. Thank you.